Okay.
Hello, everyone. A very warm welcome to another session of Computer Vision Talks, which is Vision Language Talks now. And we have been following up with announcements through mail and LinkedIn. But let's get started with the talk today. We're going to discuss something super cool, super new, something that we haven't discussed before. Um, we're going to be talking about GLOMs, which is something super cool Geoffrey Hinton came up with in 2021. And the speaker for today, Rajat, ended up making it work. And in my previous interactions with Rajat, he seems to be super dedicated and super
So,
enthusiastic about this idea. He's a fourth year PhD student at Center for Research in Computer Vision, UCF, under the supervision of Dr. Yogesh Singh Rawat. His research interests include improving the robustness of existing models, test time training, adaptation, and long term video understanding. In his free time, you can find him playing flute, guitar, hiking, exploring Buddhism, and doing meditation. And also doing some calming meditation, as we can see on the shared screen. Over to you, Rajat.
yeah.
Would you like
Okay.
to? Yeah.
Yeah. Hi. Thank you for having me here. I am not super dedicated. That's just Shambhavi overselling me. So, yeah, thank you for having me. And before I begin the talk, I would just like to say that I am not like, I don't do this often. So, if there is anything in between you want me to pause, just like feel free to ask any questions. Okay. So, I will start the talk. So this paper is titled Asynchronous Perception Machine for Test Time Training, and this was a joint work between me and my advisor, Dr. Yogesh, and this was published in Europe's last year. So we presented it in Vancouver in December. So the key point is that why am I giving this talk? So this talk is going to be very different from the ones which you generally see because most of the people when they will give a talk they will say that a lot of work is happening in transformers, neural fields, and large language models and diffusion, and most of the times their talk will revolve around one of these areas. And the way we have been doing AI since last 10 years is that the story generally people say is that you take a big model and you keep increasing the number of parameters of it, and you will keep getting a high amount of performance. So this is true, and that's what everyone is doing these days. But if you see how our brain works, our brain is, you can just eat a sandwich and then the brain is able to think in less than 50 watts every day. And that can give us human level performance in a variety of tasks. But for some reason, it is not happening in LLMs. So the trend is that what people say is that instead of trying to come up with a way to do AI in 50 watts, let's just throw more compute at the problem. So, which is like take bigger, better GPUs. But the key problem is that PhD students like me are very poor, and the resources are always a constraint for us. And we need a way to do AI which is very cheap and it is able to do as good as what a transformer can do. So generally, when we talk about cheaper models, there is always a trade-off, right? That they can't give you good performance because they are very small or something like that, and they cannot stand up against big guys. But this in this work, like what we are saying is that you can have very small model which can run in a CPU for less than $1, and you can actually do the things which all these big models are doing. So I am going to show this another way to do AI which is cheaper, faster, and better. And this talk is like one of the possible ways to do that. So you can Google a concept called model computation, which was Geoffrey Hinton's idea. I won't go into that, but this talk is about one of the possible ways to do cheap AI. So if you look at the title of the paper, it's divided into three parts. One is asynchronous perception machines for test time training. So if you break the title apart, what it says is that there is this new architecture and it's not very fancy. It's just one CNN filter and five MLP layers. And there is nothing great about this architecture, right? Just one CNN filter and five MLP layers. which makes it a 25 million parameter model. But the key point about this architecture is that it can do some weird stuff which people can't do in deep learning. And I'm going to come on that later. But assuming that this is the architecture we are talking about, this paper is concerned with test time training. So test time training. So basically we made this architecture and we showed the results on test time training. And obviously that's computer vision task. You can extend the ideas to other areas also, language modeling and other things. So the key argument being that transformers were initially worked for translation and then they came to computer vision. We have done computer vision directly, so it stands to reason that you can use it for language also. So the first thing which we are interested in is knowing what is test time training. Shambhavi, please let me know if I'm going too slow, okay?
Sure, no, it's good.
Okay, so the test time training, the key point is that the real world is always changing and we want to build models which can adapt to new situations. So for example, if you look at the way most of the people do deep learning, they say that, okay, we have a big model, we will train it on some big data set and we will freeze its weights during inference. And then in the testing phase, they generally take a lot of data and then they classify it. So you have zero shot models like CLIP. But so here the key point is that the model is frozen during training, during the inference stage, but that's not how the humans work. But the way they work is that their brains are continuously learning in real time, and that's a setting of test time training. So the model can be trained during test time also. So the idea is that you take a model which was trained on the train set and then you roll it out, you deploy it. So that's the testing phase. And during the testing, you take a particular test sample and you perform some sort of self-supervised task on that. Obviously, you can't use the label of the test sample. So generally, that SSL task you perform is something like rotation or masked image modeling or something like that. And then you update your neural network on that test sample. So the network is basically doing some sort of learning on the test sample also. And after you have done it for several iterations, you use the network to classify it. So this is a dynamic decision boundary concept in which the model is also updating its weights during the testing time. And this has been found to give us better results than just keeping the model static during training during the inference. And so there is this notion of dynamic decision boundary that your models can also adapt themselves during the learning phase, and that is what this test time training setting is about. So when you are doing SSL task, there is no label of test sample being used in the above setting. And before I proceed in this talk, I would like to differentiate between two things. One is test time training and one is test time adaptation. So what's the difference? So the first step in both the settings are same. You take a pre-trained model on train set, but there the second step is different. So in test time training, when you are processing one test sample, you will just learn on that test sample and then you will classify that, and then you will move on to the second test sample. So after you're processing each test sample, you are reinitializing the network's weights. So there is no information leakage from one test sample to another. And this is a very harsh setting. But in test time adaptation, you are looking at the entire test set and you are doing some sort of distribution matching. So we in this paper, we are concerned with the harshest setting because we want to up the stakes, and that setting is for test time training. Now, so I have told you that the architecture is very simple, and then we applied it to test time training, and I have told you the difference between TTT and TTA. Now, I told you that the architecture, even though it's simple, it's able to do some weird things which people in deep learning could not do before. So I'm going to go into those differences. So, for example, one of the key understanding in computer vision is that we need to train models on a very big data set, and that is how LXNet is trained. So you train your all the language models also on billions and trillions of samples. Now, in our case, there is a network which can just learn on one sample, and there is no neural network in the world which can just learn on one sample. But this architecture can just learn on one sample, and it does not need any pre-training. Now, the second conventional wisdom is that to learn representations, generally, you make the network do some sort of task, right? So for example, you take an image, you mask some of its regions, and your job is to reconstruct the image. Or maybe you shuffle some of the pixels of the image, your job is to regenerate the image in the correct order, which is known as the jigsaw puzzle task. In our case, we don't need any pretext task. The network is able to just learn by itself. And generally, people think that if you apply data augmentation during training, it will improve the performance. But then always there is a lot of engineering problems that how do you augment your data the best way. So what we have done is we have removed data augmentation also. And the second thing is all the LLMs and transformers are based on attention. So attention is the key workhorse which is driving the whole revolution. So in this paper, we have gotten rid of attention also, and we have come up with a better way to do machine perception. And the other problem, so if you look at the history of deep learning, earlier people came up with MLPs and then they came up with CNNs, LSTMs, and transformers. So the argument was that MLPs can't do dense image processing, so they can't process image and do tasks like segmentation or anything. And that is the reason we came up with the CNN LSTM transformer in the first place. So now we have continued this path since 1998 when LeCun invented CNNs and then Transformer when Ashish invented it in 2020, 2017. And LSTM was by Schmid-Huber in 2000. So what I am going to say is that MLPs can actually do all the things which a transformer can do and a CNN LSTM can do. And that is the thing which is the contribution of this paper. So you can imagine that we are basically going back to the dark times and we are resetting the clock to even before LXNet and even before LSTM to just say that MLPs are enough. And now I will show how you can do that. So Geoffrey Hinton came up with this paper called How to Represent Part Hole Hierarchies in a Neural Network in 2021. And this paper was saying that you can substitute everything with a MLP. And so a lot of people in Google were trying it out, but it did not work. So the whole paper I'm talking about is actually about making his idea of GLOM work. So the architecture of the network is one CNN filter, five MLPs layers, and three ideas of Geoffrey Hinton, all of which are packed into one architecture. So uh, I will, okay. So the first idea is something called location-based querying. So I want you to focus at the top half of the screen. So this is the way we generally do machine perception. We take an input image and we have any model. This model can be a transformer or it can be any model like a CNN. So generally what happens is that when you give it an input image, out comes a rectangular feature grid. So this grid is a cuboid. And you can imagine that this model has a lot of layers, like 24 layers or 36 layers, even 98 layers. And all of those layers are attention layers. And up at the end of your model, you finally get this cuboid. So you can look at this representation as a cuboid. Now it does not matter what your model is. If you can directly learn a mapping from input to the final layer cuboid, that's all you need. If you can get from the image to this cuboid very fast, then it doesn't matter what this model is because you only use the features of the last layer to do any downstream task. So now there is a new way to interpret this feature grid, and the way is as follows. So instead of looking at this as a cuboid, you can look at it as a lot of tiny, tiny vectors, which are like along this direction of the screen, which are lying there. Shambhavi, can you see my cursor?
Yes, I can. Yeah.
Okay. So you can imagine that there are these vectors here. So here, if this image is of height cross width cross d cuboid, then you can imagine that there are height into width such vectors of d dimensions each. So you can imagine that there are two locations, and for each location, there is a d-dimensional vector. So instead of predicting this cuboid, we can imagine that there is a new type of model. And the way it works is it takes an entire image as input and you query it with location 1, comma 1. And it can directly give you the red vector at this location. So what happens is that if you query this network height into width times, So for each location, if you query it one by one, you can basically predict this whole grid in parallel. So in the above case, you made one feed forward through the network and you got the rectangular grid in a single shot. But in the bottom case, what you do is you query it one by one and you can get these vectors along D dimension one by one. So the key benefit of this is that it is entirely parallelizable. So for height cross width locations, you can generate these d-dimensional vectors in parallel to each other, which makes it very fast as compared to attention. So is this clear? And or does anyone have any doubt?
I think to me so far it's good. We can move to the next part.
Okay. So the next part about this model is that the model at the bottom is something called a coordinate-based network. So now the key point is how do you learn this? How do you learn this network? So if you have a image, so if you have this grid and this is a teacher, like say let's say Dino V2 or Dino V1, and it has a vector at this location, you can directly distill this network, you can directly distill this knowledge into this network at the bottom. So essentially what will happen is that if you have a bunch of images, your network at the student will learn to mimic the vector at each location, and it will start predicting the same feature which a big model is predicting. So essentially after you have learned to mimic the feature grid, you can substitute the teacher's model with the model below. Now, here is the key point that the model, which is the student model, which is the teacher model, is basically having 20 or 100 layers, but the model which is below is just a MLP, which consists of 5 layers. So it's extremely efficient and it directly learns a mapping from input to the last layer grid.
I
So
have a
here
question.
yeah, sure.
Here is the performance of this student APM, which is a very low level MLP, dependent on the quality of teacher, right? Like if you're
Yes.
distilling it from clip, it will be very good. But if you're distilling it from a smaller LSTM based network, it might not be so robust, right?
Yeah, it might not be, but the key point is it will always be better than the teacher,
I see. Okay.
but its performance will depend on the teacher, but it will improve upon the teacher.
Okay. I get it. So this kind of
Okay.
setup might be like super advantageous in a setting where you have a LLM and you don't have the cost to retrain it and you want a faster inference. This kind of
Yes.
yeah, okay. Okay, makes
Yes.
sense.
So now here I'm showing the inference time versus number of patches. So here if you see, you could query the model at the bottom with location 1, 1, 2, 2, 3, 3, 4, 4. So you could query individual patches in it. So, but in a transformer, you cannot query patches because its attention, it's entirely parallel. So the network can't break a patch size of 224 in any lower number of patches. So in a clip VIT-B16, it takes 2.2 seconds for inference. But in case of our network, because you are querying each location parallelly, so all these locations become the batch dimension. So there are height into width such queries, and it takes around 0.02 seconds, which is basically a thousand-fold speed up in time as compared to the parallel perception, which a normal transformer was doing. But the key point is that the features you predict are the same as transformer and even better sometimes because you learned it from the transformer itself. So that's the key point, which gives it a very fast speed up as compared to a transformer. Now, the third idea about how the network works is this idea called folding unfolding. So what I want you to start thinking about the network is something like this. So it contains one CNN filter and one MLP layer. And here you are generating height into width number of queries to the input. So this column is copied height into width number of times. And for each column, it gives you the feature vector and the RGB at that location. So if I were to interpolate here for this location 1, 1, it's giving you this vector. So this column is basically the query corresponding to 1, 1, and the output is corresponding to this d-dimensional feature vector. So the way it works is there will be one of such columns, ti minus 1, let's say it's for location 1, comma 1. The MLP will look at that column and it will predict the red colored vector for that location, which I showed in this figure. So now if you have 100 such locations, the MLP is shared across all such locations. And for each location, it's predicting the feature vector and the RGB value at that location. So now there is a problem, right? If you feed input image to a MLP, it does not work because let's say your MLP's first layer has 100 neurons and the MLP's second layer has 10 neurons. So as soon as these 100 neurons are connected to the 10 neurons, the information gets intermixed. So if you were to take a MLP and if you were to input an image to it, then what will happen is all the information is mixed after the first layer because it's a dense connection, right? Every neuron is connected to every neuron up, and then what will happen is you can't train a MLP to do image reconstruction. And that's why there is no MLP in the world which can take an input image as input and give the same image as output. So there is no MLP which can be trained for image reconstruction. The best the MLP can do is it can be used for classification, for example, MNIST and or CFAR 10. But on CFAR also, it will give you just 50% accuracy. It won't give you 100% or 99% accuracy, which a CNN would give you. So that is the fundamental assumption that because the information is mixed beyond the first layer itself, that's why the MLP does not work well. So this is the way people have been feeding the data to MLP since the last 20 years, or even 30 years since MLPs were invented. So we have changed the way you feed the data to the MLP to make the MLP work for images now. So now I will give you a biological analogy and that will help you understand the network. So consider how a baby is born. Okay, so you have a sperm, you have a zygote, and after the intercourse, it forms a cell. That cell is known as the zygote. So every cell in your body has the same DNA. But depending on the DNA, sometimes the body gives you the nose, and sometimes your body has the eye, and sometimes it gives you a mouth. So that's the whole idea here. So the idea is that, for example, if you are given four of such tokens, so let's say you have an image and you partition it into four tokens, and your job is to predict the nose now. So you want the network to learn that at third location there is a nose. So you want the network to solve this task, and that is what the MLP does. So the way you make the MLP work is, so let's say you have a sequence of images and sometimes you want it to predict an eye, sometimes you want it to predict an ear, sometimes you want it to predict a nose, and sometimes you want it to predict a collar. So the way you input this data to the MLP is you take this image and you flatten it. So there are four locations. So there are four locations and each of the location contains the entire image. And you have four locations, so you have four numbers, which are the positional encodings 1, 2, 3, 4. So if you look at this column, what the MLP is trying to do is there is an image and it is trying to predict what is present at location 3, which is the nose. Similarly, if the MLP looks at this column, there is the whole image, and I am trying to predict what's at location 4, which is this collar. So the MLP will try to predict the collar. So this is the architecture, and just by changing this way, the MLP is able to reconstruct RGB of any image in the wild. So as you can see, the MLP is able to process all of these columns independently now. And sometimes it will give you an ear, sometimes it will give you a nose. So this is equal to how different locations in your body contain the same DNA, and sometimes depending on the location you get an eye or a ear. So is this clear, or should I are there any doubts in this key process?
No, so far. To me, it's understandable. If there's any doubts, people can post it in the chat and I'll let you unmute you and have the discussion forward.
Okay, so now I want you to look at any of the columns of this figure. So let's say we are looking at this column. So this column contains two things. It contains the position and it contains the image, the entire image. So this is a generic data structure which is being fed to the MLP. So this column contains, you can think of it as a cell in your body. It contains the image, the DNA, and it contains the position. And the network is trying to solve what component of the image is present at this location. For example, in this case, it's trying to predict so in this whole image, what is present at location 2, which is the ear. So that's the key change we have made. So this is a different way to feed data to a MLP. So let's call this data structure as trigger column. And now let me show you how the network is working. So the first step is that you take an image. So let's say your image is 100 by 100 by 3 channels, and you have just one filter. And let's say your image gets down to 10 by 10 by 1. So you flatten those 10 by 10 numbers to 100 numbers. So those 100 numbers are this I, and you're trying to predict something at location 1. So this number 1 is not an integer, it can be a hard-coded positional encoding from a transformer. So maybe there are 100 numbers corresponding to location 1. So in this case, this column contains 100 numbers for image and 100 numbers for location 1, which is 200 numbers. So the first layer of the MLP will contain 200 number of neurons. So in this diagram, I was showing you 4 columns. So the way these columns work is, so from one CNN filter, you have this I image, and then you generate this location, which is hard-coded number, which is 1. So you can create 4 such queries. So all of these queries have the image I, which is common to them. And this 1, 2, 3, 4 are not any learned parameters. They are hard-coded positional encodings, which you sample from a transformer. So I call this, so the learnable parameters in this whole network are only in one CNN filter. You take the image, you route the representation to it, and then you copy it many times, which is equal to the number of locations in the image, and you attach a hard-coded positional encoding every time. So before your forward pass, your network just contains one CNN filter. And after the forward pass, this filter gets copied and it gives you 4 such queries. And then what happens? So this process is folding because right now there is no query existing. So the entire network is in a folded state. And then during forward pass, it opens up to give you these queries, which is known as unfolding. And then you run a MLP on the top of it, and it will give you the features. So the forward pass looks like folded, unfolded, folded, unfolded, and every time the network is predicting RGB. So now this is true to this figure which I showed earlier. So the network is oscillating between a folded state and unfolded state. So another point I would like to mention is that folding, unfolding is the same concept which is used in chemistry also in the paper of AlphaFold, by which the proteins fold themselves from amino acid sequences. And that's the whole idea which we use in the machine perception community now. So now the key point is, how do you train this network? So the way you train this network is that you start from a folded state. So at that time, you just have one CNN filter, one MLP, and one image, and then you expand it. So there are 3 such queries, and you feed the input image through the CNN filter. You have height into width locations, and you're trying to predict the image again. You're trying to make the MLP reconstruct the image back. So this is a cyclic learning process, and it's self-supervised because the loss here is just L2. You're trying to predict the same image you fed in. And I would also like to say that we have used such inductive bias earlier in some architectures like masked autoencoding and other places like that. So you do this RGB reconstruction for a bunch of images, and then what will happen is that this MLP will start doing some magic, which I will explain now. So let's say that you have trained this system on a bunch of images, and you have one image and you have another image, and you route it through this CNN filter, and you get 2 representations, which is vector v1 and v2. So what will happen is that you can generate intermediate vector representations between these 2 vectors, which is v1 plus v2 minus v1 by n. So this is just a linear interpolation. So you will feed this higher dimensional latent into this network. And now your job is to predict RGB using that intermediate latent. So what will happen is that if you take any two images, the MLP is now able to interpolate between any two images of the world. So this is a generative property, and till now we were able to see it in GAN and diffusion models. But after you train a MLP by this folded unfolded concept, what happens is that take any two images and you are able to interpolate between them. So this is very surprising because we didn't want to build a generative model, and this is just a side effect for that. So what I'm trying to say here is that you can use the MLP to substitute for what a diffusion model is doing. So another thing which happens is that if you feed a black and white image to the MLP, it becomes colored. Now, so I have explained how you I
There's
have
a
explained the
question. Sorry, there's a question in the chat that this is observed. This was not planned, right?
yes. So this color, so this taking these two images and this ability to interpolate was never planned, but this is what emergent which emerged in the network.
I see. One more question that you're talking about transitions between folded and folded states. I am not sure if it will. I have a doubt that, like, do you have stability concerns in it, like, to
No.
balance states? No, there's no loss of information happening when you're folding. And
Yeah, no, there is no loss of information happening because the reason there is no loss of information happening is because all the information is in this CNN filter. So when we are unfolding, when we are copying this CNN filters contents, we are actually
mm,
creating information. And the information is created, but it's not created out of nowhere because this I is shared across the columns. And this 1, 2, 3, 4 are hard coded integers. So that's why the information is not getting. So the CNN filter receives gradients from all the locations, which does
right,
not yield in any loss.
I see. Okay, okay. And there's another question in the chat. Does it generate high quality images because the transformation between folded and unfolded state is lossy?
Yes, you can generate very high quality images using it. In fact, we have tested it can generate images up to 1024 by 1024 resolution.
Yeah, but is it because the transformations are lossy, folded and unfolded?
So they are not lossy. So if you actually
Okay.
scale this up to 1024 by 1024 and you train it to do RGB reconstruction on a lot of images, you can actually see very clear pictures.
Okay, I see. Okay.
Okay, thank you. So
Um,
the reason they don't appear so beautiful here is because I trained this network on 32 by 32 images because I don't have that many resources. But
and what
that
was your
does not.
patch size?
So my original image was 448 by 448 and my kernel was 8, 14. So the resultant output is 32 by 32. But you can always
Mm-hmm.
keep a kernel size of 1.
I see. Okay.
Okay,
Interesting. Okay,
thank
let's
you.
move.
Okay, so we have seen that you could train this network on a bunch of images, which is taking a lot of images. But now let's talk about a new property, which is you can learn this network on just one sample, which is a property no other architecture can do. So now let me explain how do you do test time training using this architecture. So for test time training, we have two things. We have a teacher and we have a student. Now this student is the network, which is this new network, which uses this folded unfolding operation, which I told you, and it will do test time training using a teacher, and it will improve the performance of the teacher. So as Shambhavi correctly mentioned, the performance will depend on the quality of the teacher, but the trade-off is if your teacher is very nice, you will get an even nicer performance after doing test time training. So now let me tell you how to do the test time training. So let's say you are running this for every test sample, you are doing 20 iterations of test time training. So during the first iteration of test time training, you will feed forward this entire image through the vision encoder of clip, let's say. And let's say it gives you a feature vector F, which for all sense and purposes a single vector, which is a CLS token. Let's call it a 768 dimensional vector. So the feed forward through the vision encoder is only done during the first iteration of test time training. And after that, we can discard this vision encoder. Okay. Now for for 20 iterations, what we will do is we will feed this image through our network to get the feature f dash. And the loss you are using to train the network is basically you're trying to make this f dash as similar to f as possible. So it's just a L2 loss. There is no self-supervised learning. There is no SSL task you are doing here. You are just trying to predict this same feature f. So you're trying to make f dash equal to f approximately. So you do this for 20 iterations, and then what you do is you use the teacher's textual encoder to classify the sample. So once you have started predicting nice features f dash after 20 iterations, you will actually predict the same. You become aligned to the teacher's textual encoder in the contrastive space. So you can use the teacher's textual encoder to do a direct zero shot classification. And once you have done that, then you move on to the second test sample and you can reset the weights of this whole network. So now here is the good thing that if you look at this network, and you give it a CLS token of any image, it will overfit on that very nicely. And then your L2 loss will go very down up to 10 to the power minus 12. And then it can do zero shot classification. So this is how you do test time training. And it actually scales up to, so if you look at the results for test time training, the best model of open clip on ImageNet is 81.6. So this was pre-trained on 5 billion image text pairs, but it was never pre-trained on ImageNet. So that's why there is a cross here. So using the open clip VIT huge as a teacher, we can actually use test time training and improve its performance by 3%. So that's the selling point, and you can see consistent gains across all the ImageNet splits. And similarly, you can see it across all the noises of ImageNet C. ImageNet corrupted. ImageNet corrupted is just 50,000 test samples, but they are subjected to different noise severities. So I am showing this for 15 of such things. So for 15 such noises, and it will also generalize to other data sets. So in this case, we were able to outperform, I think, 5 of all the data sets which are present here. So consistent gains with this network. Now, here is some visualizations which I would like to say. So APM is just one MLP, right? It's just one MLP with one CNN filter. Now, this is a very nice analysis which you can see. So let's say you have an input image and you pass it through Dino V2. And so your Dino V2 will give you height cross width cross D-dimensional feature grid. So what I am plotting here is TSNE reduction of that height cross width cross D feature grid to 3 dimensions. So everything is color here. So all the colors here represent the same object. So that this is the feature grid of Dino V2, and this is the feature grid which APM can give you when you are using a MLP. So normally MLPs can't predict feature grids like this. So now if you calculate an error map between this grid, you get some error, but there is not a lot of error. Most of it is black, which means that you are approximately able to approximate the features of Dino V2. But in fact, your features are better than Dino, and that is why you were able to surpass the performance of the teacher by 3%. So now, in conclusion, in this paper, like we have introduced this new mechanism called folding unfolding, and that is what is making the whole network work. It can learn on one sample. Now, the next thing which we are doing right now is that we have removed the deep learning also. So now consider, let's say your network has 10 layers and you want to predict the feature at the 10th layer. So the only way you can predict the feature at 10th layer is by making a forward pass through the previous 9 layers and then the 10th layer. So the amount of time it takes you to compute the features at any layer is basically the amount of depth the layer is in your network. And that is how deep learning has worked. But what we have actually done is we have made that time a constant. So we can query the features of any layer in constant amount of time, and it does not matter how deep it is. And in fact, we are seeing very nice results using that. and that is something we are planning to submit in the NeurIFs this year. And we are also trying to overcome the problem of backpropagation and trying to replace. So the problem with backpropagation is that if your network is very deep, then what happens is that the first tier has to wait for the gradients from the last tier to come back. So if your network is very deep, then the network is not able to learn very fast. So instead, we are using Hinton's new idea of forward propagation there. And yeah, there are some of these cool insights which we are trying to work on. Yeah, thank you. So that's all from my end.
Great. That was a great presentation. I do have a few questions. Maybe you can keep the screen from the presentation. I don't want to see myself, or maybe stop sharing. Whatever works.
Oh, okay, I can stop sharing.
Yeah, this is good. Like, let it be on the minion screen. It's good. Okay.
Okay.
No worries. Yeah, right. So it was an interesting presentation. We do have some comment in the chat from Kunal about high quality images should be SSIM and PSNR to define the high quality.
Yes. So we actually did one experiment where we compared the LXNet score on it. So I forget it. It's SSIM. So we see a very good performance in that metric. We didn't do FID and other methods because the paper was focused on test time training.
Mhm. Okay, I see. Also, one natural question that comes to my head is that given that right now the way industry is progressing with LLMs, this could be something super interesting to just try for inference time.
Yes.
And are you extending it to, like, I can understand the compute constraints for sure, but is there a plan to have this on top of say llama like model to just check how well the distillation performs at inference time?
Yes, that's a very interesting idea. So we are actually having some projects on that, but I don't have any results to show right now. But yeah, we do observe very good performance there.
Okay, okay, interesting. And okay, let me just keep this on the screen. Right. So there's one more comment in the chat. Can you address that one from Kunal as well?
Um, it says if you claim high quality reconstruction, can you check for style, GAN, etc., like high quality generative methods? So we never claimed high quality reconstruction in our paper. We just claimed that we can make a MLP reconstruct an input image. And we never said that we are comparing with generative techniques. But we are just saying that there is a potential for generative behavior, but we are not, our aim is just to do test time training right now. But yeah, that would be a very interesting direction.
Yeah. And in the longer run of things, do you think there's a scope of self-supervised distillation from APM to APM itself? No.
Yes.
Okay. Okay. Um, I see. Okay. Yeah, I think these were my questions, more or less. And you didn't have any specificity to choose TTT as a task, right? It was just because it fits the schedule.
S- Yes. So the key point was that it is able to learn on one sample and it does not require any pre-training. So that's why we chose test time training because it learns on one sample.
And if you have to extend it to huge batches, how would it scale?
So it scales really well. So I had actually a slide in which I was training it on a bunch of images. So that network was actually trained on Coco.
Yeah. Okay.
So you can do it because you can essentially predict the same features a transformer is predicting. So you can learn it through distillation and then substitute the transformer backbone to do anything. But it requires a lot of resources, so I didn't check it.
Okay. Interesting. Yeah, this sounds interesting. This is definitely something I want to explore further and read more about. Uh, Yeah, these were questions from my end, and I see that people in chat don't have more questions either. So, thank you so much, Rajat, for the interesting talk. Although
Thank you.
it does exist previously recorded, but I still wanted to have a discussion with you on the paper. And I think it should be discussed more. I think it can really help some industry use cases right now, the way people are evolving with the LLMs in particular.
Yeah,
Right.
thank
Yeah.
you.
Thank you so much for presenting, and thank you for the audience to showing up on a Saturday morning. And a very happy Holi to everyone who's celebrating. Thank you.
Thank you.